So in previous lecture we have finished with the chemical potential. Now next is the Gibbs Duhem equation. Okay, so this is the important equation for the finding out the chemical potential for the binary solution or the binary mixtures. Okay, so in order to find out the chemical potential for the binary mixture, we will again consider the that partial molar property or the simply chemical potential. Okay, now consider the system which is having the N1, N2, N3 as such number of moles for the different component at a certain pressure value P and the temperature value T. Now the free energy change, that is dG, which is given by what? dG is equals to dG upon dP at constant temperature and number of moles, dG upon dt at constant pressure and number of moles, then dG upon dN1 at constant temperature, pressure as well as other constant of the number of moles. Okay, likewise we can have the various changes in the Gibbs free energy with change in the number of moles for that particular component. Now at constant temperature and pressure we can simply neglect these two terms, so we have been left with only what? This term into dN1, this term into dN2 likewise. So what is this term? This is simply the partial molar Gibbs free energy, which is also called as what? The chemical potential. Okay, so we will represent it by the mu1, which is the chemical potential of first component, that is mu1 into dN1, mu2 into dN2. So this is the, suppose this is the equation number 1.52. now upon integrating that equation we just need to like integrate. So instead of this derivative get cancel out here, this also derivative get cancel, so we have been left with only what? mu1 n1 plus mu2 n2 plus mu3 n3 likewise. Now upon general differentiation of the above equation, so this dg is equals to what? For this you need to use the UV rule of multiplication for differentiation, that is mu1 into dn1 plus n1 into d mu1. Okay, now here mu2 into dn2 plus n2 into d mu2, right? Now next up to here we can have the say I term. Okay, so we are not going into this whole, so up to this we are sufficient because we are studying it for the binary solution, right? Now upon rearranging the equations, that is dg is equals to, so simply rearrange that equation in such a manner that one term containing the dn1 dn2 likewise they are on the one side or one bracket, and other term are on the another bracket. Okay, now we know that this dg upon dp dg is equals to this plus this term. Okay, now but this term is what? This term is the again same term like we have seen in this equation here. So this term is equals to what? dg again. So here we can simply substitute that for this term dg, here also dg, so this and this get cancel out, so we have been left with only what? n1 d mu1 plus n2 d mu2 plus n3 d mu3 up to so on is equals to 0. Okay, or we can simply say that summation of ni d mu y, summation of ni d mu y is equals to 0. So this is the important relation of the Gibbs Duhem equation. This equation is useful for calculating the chemical potential for the binary solutions. Okay, so this equation is called as a Gibbs Duhem equation. It is quite important for studying the chemical potential of binary system, solutions, liquid vapors, equilibria as well as the phase equilibria. So whenever there are the two components and if we need to find out the chemical potential of that particular system, so we can obtain that chemical potential by using this Gibbs Duhem equation. Now consider the two component system for the above equation, that is n1 d mu1 plus n2 d mu2 is equals to 0, that is n1 d mu1 is equals to minus of n2 d mu2, or d mu1 is equals to minus of n2 upon n1 into d mu2. So this is just the simply rearrangement of the given equation. So we can derive that equation anytime, but first of all we should know this equation, that is ni d mu y is equals to 0. Now above equation shows that the change of one component potential during the process changes the potential in the other component of the system also. Okay, so here you can see this. So if we change the value of d mu2, ultimately the value of d mu1 is going to change. Okay, now the negative sign is there in the equation, which indicates that what, the chemical potential of one component increases, then the chemical potential of other one should get decrease. Okay, but the total sum of change in chemical potential is what, always 0. Now consider the problem related with this uh, chemical potential and the Gibbs Duhem equation. Now we are given with the solution containing the 22.6 gram of aqueous solution of ethanol, which containing 44.6 gram of ethanol. Okay, if the change of chemical potential of ethanol is 10 kilojoule, then find the change in chemical potential of the water. Now we have been given with the 4.6 gram of ethanol, so the remaining one is the solvent molecule, that is water molecules. How much remaining? So that is around 18 gram. Now we need to find out the number of moles. How will you find out that number of moles? So for that we will require the mass upon molar mass. So we have been given with 4.6 gram of ethanol, which is, and the molar mass of the ethanol is 46 gram per mole. So we have been obtained that value as a 0.1 mole of ethanol, and for water it is 18 upon 18, which is 1 mole of water. Now first we have given the chemical potential for ethanol is d mu1, which is minus 10 kilojoule. Okay, now we need to find out the value of this d mu2, that is change in chemical potential for the water. Now we have the standard formula of n1 d mu1 plus n2 d mu2, that is 0.1 into minus 10 plus 1 into d mu2, which is we need to find out, which is comes out to what, 1 kilojoule. Okay, so that is the chemical potential of water is increased by 1 kilojoule. Okay, so positive sign indicate that the that chemical potential is increased for the water. Now next important derivation is the variation in the chemical potential with respect to pressure and with respect to temperature. Okay, now we have already studied this for the Gibbs free energy, but that Gibbs free energy relationships are studied for the closed system. Okay, so with change in the pressure, we will be obtain the two important relations. Okay, Gibbs free energy change with respect to pressure and Gibbs free energy with respect to temperature. Okay, there we have obtained that for first change in pressure it is volume, and for change in temperature it is minus of entropy. Okay, likewise we will be obtaining the change in chemical potential with respect to pressure and temperature. Now any change in the given system at constant pressure and temperature are proceed from the higher free energy state to the lower free energy state. Therefore the Gibbs free energy taken is as the thermodynamic potential, and any change in the system is proceeding from the higher thermodynamic potential to the lower thermodynamic potential. Okay, now this concept is valid only for the closed system if you are considering only the Gibbs free energy. Now that is means for closed system is what, for the system which containing the same or constant composition, means number of moles for that particular system is constant, kept constant. Okay, but now Gibbs has applied this concept of chemical potential, which is being the intensive property, which is independent of what, the number of moles, for the study of open system. Okay, now this chemical potential or chemical potential mu, which can be applied for the open system, because this chemical potential is what, the intensive property, so it is independent of, obviously it is independent of what, the number of moles. Now in the thermodynamic study of the open system, it is quite necessary to find the contribution of the each component to the total value of given thermodynamic property of the system. The chemical potential mu of any component in the given system is the number of component, which is defined as what, the change of free energy of that particular system upon addition of 1 mole of that particular component at constant temperature and pressure to such a large quantity that the system's value are practically unchanged. Okay, so this is the quite definition of our partial molar properties, so that we have already studied that. Okay, now we will study the chemical potential change with respect to temperature and pressure. Now what is the value of mu1? The value of mu1 is simply the dg upon dn1 with keeping the temperature, pressure and other number of moles constant one. What is the value of mu2, which is dg upon d into keeping t, p, n1, n3 as such, all the other value constant. Okay, now the chemical potential is being what, the intensive property of a system, and it will have the same value throughout the system at equilibrium. Change in the system at constant pressure and constant temperature will proceed from the state of higher chemical potential to the lower chemical potential until its values become uniform throughout the system. So this is quite uh, observed relation for the all the system. Okay, all the uh, spontaneous systems. So for 1 mole of a pure substance, the chemical potential and the Gibbs free energy are equal. That is, we have already obtained this relation also. That is, for the pure component, this Gibbs free energy and chemical potential are equal. Okay, now first consider the variation of chemical potential with the pressure value. Now the chemical potential change for the given component is given by what, this formula, that is mu is equals to simply dg upon dn. So we are not considering any particular or any specific number of component, we just considering the general formula. Okay, now if we change the pressure for this system, what will be the equation? So just simply differentiate the above equation with respect to dp. So that is d mu upon dp is equals to d by dp of dab g upon dab n at constant temperature. By using this Euler's identity, we can simply rearrange that equation as dab by dab n of dg upon dp. Okay, so give this as equation number say 1.60. Now as we have already derived one equation, that is what, this is the important equation that we have already say this, and various forms of this equation are quite useful for deriving the other terms also. So again we will use this equation. So the dg is equals to what, vdp minus sdt, but at constant temperature this dg is equals to vdp or dabba by dabba d by dg of p. At constant temperature is comes up to what, v. Now substituting that value of v in the given equation number 1.60, so that is d mu upon dp is equals to d by dn of v, which is equals to what, v bar, because this term is what, partial molar volume. So we can say that this change in potential, chemical potential with respect to change in pressure is equals to partial molar volume. Okay, so this shows that the change in chemical potential with respect to pressure is partial molar volume. Now applying the general gas equation, this is the differential form of chemical potential and pressure relation. To obtain the integrated form, we will just simply apply what, the gas equation, general gas equation, that is PV is equals to nRT, and this dV upon dN is equals to what, RT upon P, which is equals to V bar. Okay, now just simply substitute the value for V bar here. So that is d mu upon dP is equals to RT upon P. Now upon integrating the above equation, that is d mu is equals to integration of RT upon P Tp, and we know that the integration is what, the integration is ln of p, that's natural log of p plus some constant. Okay, so we need to find out the constant. So how we can find out that constant? So consider at this condition for the, at standard condition of temperature and pressure, that is at 1 atmospheric pressure, this term will get 0. Okay, because the log of 1 is 0, so the value of mu, that is the chemical potential, is having the certain constant value. So that now we can say that this mu is equals to what, mu 0 plus RT ln of P, that is chemical potential of a system is depending upon the pressure. Okay, so this is the one relation, that is the dependence of chemical potential on the pressure value. Now next is the variation of chemical potential with the temperature. Okay, so this chemical potential value again is changes with the change in temperature with the fixed pressure value. So mu will be the change in temperature. So we will consider first again that mu is equals to what, dg upon dn. Now again differentiate this equation with respect to temperature at constant pressure, that is d mu upon dt at constant pressure is equals to d by dt of dg upon dnp is equals to, again using the Euler's identity, that is d by dn of dg upon dt. And we have already derived this for dg upon dt at constant pressure is comes out to be what, minus of s, that is minus of entropy. Now substituting that value here, so we will get what, d mu upon dt is equals to d by dn of minus of s, or simply it is minus of s bar, that is the partial molar entropy. Okay, so previously we have obtained the value for partial molar volume, partial molar pressure, then partial molar free energy, that is chemical potential. Now we have got the value for partial molar entropy. Okay, so the change in chemical potential with temperature is simply the partial molar entropy of the given system. Okay, so sometime you might be asked about the partial molar entropy, so it should be the change in chemical potential with respect to change in temperature. Okay, so now from next lecture onwards we will start with the new concept, that is the fugacity and the activity for the gaseous mixture. Okay, or for the gaseous real gases. Okay, simply.